That's a good effort. Okay, welcome back, guys. My apologies for the delay, but I did have some stuff I need to take care of. But anyway, we'll keep it short. We won't go the full time. We'll stop at 5:30. Couple of quick things. We are in chapter 14 right now. Obviously, we've got one more chapter. This chapter probably would take a couple of sessions. And then the next chapter, the last one, fairly short. Anyway, if you look at the schedule, we are basically going to have a lot of time at the end here. We'll be done way before the end of the semester. So I'm going to split that up. So basically, we're going to do like lecture on one day and then study day, if you will. I'll be here. You come in with any questions you want. Get you ready for the final, which will be, obviously, actually in a few weeks. We are in week 12, I believe. Week 12. So, and then the other thing, it went past me, I forgot. Tomorrow, or Thursday, I should say, we won't have class due to Veterans Day. Okay, so no need to show up. I won't be here. Anyway, any questions? Any questions about where we're at, what's going on, anything of the sort? No. Okay, I'm letting in some people here. So don't forget today we have the exam. It's open to 11. So take your time, give yourself plenty of time like before, okay? Approximately same number of questions. So give yourself plenty of time. Please don't wait until, last hour or 10 o'clock because you're given, 75 minutes. So, and let's see what else. That's about it. Any questions, comments, concerns? Yeah. Okay, well, this brings us to chapter 14. Now, remember what we did in the previous chapters with respect to Lewis dot structures, okay? Remember we worked on making Lewis dot structures. We talked about polar bonds and nonpolar bonds. We talked about how we can put use the Lewis dot structure to figure out, to help us determine whether the molecule is polar or nonpolar, okay? Because this is where we need to use that information. This chapter deals with what are called intermolecular forces. These are interactions that occur between molecules and how they interact with other molecules of themselves. Other molecules in general. We're going to kind of narrow it to other of the same molecules. And that effect has, how we determine what effect they have. We have these forces, specifically 4 of them. And to assign molecules a specific force, we have to go back a little bit and refresh our memory about polar bonds. We're talking mostly about covalent compounds, but there are some ionic compounds in here, but very little. Most of it has to do with covalent compounds. Obviously, we're dealing with nonmetals. And so from there, we look at the bond, right? And we see that the bond is either going to be either equal sharing or non-equal sharing, which then tells us whether we have a polar bond or a non-polar bond. Now, in the general guideline, if the molecule has nothing but non-polar bonds, okay, and that's it, that molecule as a whole is a non-polar species. We need to know that because once we determine the polarity of the molecule, we can assign one of these forces we're going to talk about. So the molecule has all non-polar bonds. Boom, we got a non-polar compound. Now, what happens if the bonds are polar? And remember, in general guideline to help you is that when you have two atoms that are bonded and are the same, like A bonded to A, we had the same element, okay? They each have the same quantity we talked about, which was the electronegativity. Remember that? Electronegativity was a measure of the affinity for an atom to pull electrons onto itself of a bonded atom, okay? And so when the electronegativity are the same, then we have equal sharing. When we have equal sharing, we have a non-polar molecule. Okay, so if all the bonds are nonpolar, then we have a nonpolar molecule. The other example of a nonpolar molecule, recall, is the carbon-hydrogen bond. Okay, nonpolar bond, even though they're different atoms, because the electronegativity of carbon-hydrogen is essentially the same, we treat it as a nonpolar bond. Okay, now when you have A bonded to B, which is a totally different element, totally different, without question, you have a polar bond. Okay, you have a polar bond because now you have unequal sharing of that bond between A and B. And because there's a difference in electronegativity, okay? And the direction that it pulls depends on the electronegativity of A or B, which one's stronger. And we determine that from its position relative to fluorine, because fluorine is the most electronegative element. And so for argument's sake, let's say that B is a lot more polar, has a higher electronegativity. So recall that arrow that we drew point toward B, which meant that B had a partial negative and A had a partial positive. It has a dipole, two poles, a north and a south, so to speak, in this case, a negative and a positive. And so in the general statement is this, that when you have a molecule that have all nonpolar bonds, all polar bonds, you end up with a polar molecule unless those polar bonds cancel each other out, okay? And we had things like carbon dioxide. If you recall carbon dioxide, we draw the Lewis structure, and that's where the Lewis structure comes into play. You have to figure out where there's polar in that. We know that there's a polar bond between carbon and oxygen in both directions, okay? And so we would think, okay, two polar bonds, we get a polar molecule, but it's not the case. In this case, the polar bonds are going in opposite direction. They cancel out. Therefore, carbon dioxide is an example of a species that has polar bonds, but is overall nonpolar because the polar bonds cancel out, okay? Another one was when you have polar bonds in tetrahedral, where you have, let's say, carbon tetrafluoride, that because of the tetrahedral configuration, yes, you have four polar bonds, but because of the tetrahedral configuration, they all cancel each other out, and you end up with a nonpolar species. So polar bonds normally give you polar molecules unless those polar bonds get canceled out with each other, and then you end up with a nonpolar species. So you need to go back and rehash this Lewis dot structures, electronegativity, polar and nonpolar covalent bonds, because we need that information to assign to it some type of intermolecular force. And once we know that information, we can do some prediction when we're comparing two different compounds. We can do some prediction with respect to physical properties such like boiling point. Who's got the greater boiling point? We won't be able to determine, give absolute values, all we can do is give relative values, okay, with respect to something like boiling point, surface tension, and we'll have more on that here in a bit, okay? All right, so the difference between intermolecular forces and intra, I-N-T-R-A versus I-N-T-E-R. Now, I-N-T-R-A simply is the forces that keep an atom or molecule together. They're dealing with basically the bond within the molecule, within the compound, okay? Whereas intermolecular forces deals with the interactions, denoted here by the dotted line, of molecules with each other, okay? Now, you might think about this for a second. If you had a series of magnets, north-south pole, and you were able to line them up, that, you know, they're arbitrary in different directions, but you had a method to line them up, they're going to line up, you know, north to south, north to south, north to south because of the pole. Well, guess what? When we got polar molecules, because of the partial positive and the partial negative, they're going to do the same thing. They're going to interact in that particular manner, okay? And we will learn a little bit more about that here in a bit. Now, don't confuse these intermolecular forces with a chemical bond, because the IMF interactions are definitely weaker than an actual bond, okay? We're not trying to compare the two. We're just comparing the interaction within molecules with each other. Okay. Now, you can see here as an example, we have hydrochloric acid, HCl. We know this is a polar molecule. Why? 2.1. Two different atoms, hydrogen and chloride bonded together, automatically polar molecule. Okay, that's it. And it's not carbon hydrogen. If it's carbon hydrogen, non-polar all the time. But anything else, polar molecule. Okay, it has a dipole. We know that chlorine, being closer to fluorine, is a lot more electronegative. Therefore, the dipole arrow goes toward the chloride, which means that there's a partial negative on the chloride side and a partial positive on the hydrogen side, okay? And that causes these molecules to interact as follows. Yeah. Obviously, the negative, partial negative is going to attract the partial positive side, and they're going to line up. Now, and we're going to create this interaction right here. It's a pretty strong interaction. For example, water is a very polar species. It takes it takes 100 degrees temperature to get water to boil, okay? But other molecules that have water-like properties boil at a much lower temperature, like ethanol. Ethanol has some water properties, but ethanol boils about in the 78 degrees Celsius range, okay? Its interactions are a little bit weaker, so it doesn't take as much energy to break up that dotted line there. Okay, so that's those intramolecular forces. Okay, there are 4 types of intermolecular forces. Okay, the very first type, it is what we call the London dispersion forces. London dispersion forces. This is only occurs for molecules that are non-polar only. Okay, and so once you take a molecule and you determine that that molecule is non-polar, then automatically the only intermolecular force it has is the London dispersion forces, LDF. Okay, they are the weakest forces that are there. The next one is called dipole-dipole forces. Well, first of all, the requirement for this to have is, one, you're going to have a polar molecule. Okay. polar molecule. And if, for example, this is partial negative, this is partial positive, it's going to interact with another AB with a partial positive tail there and a partial negative. And so just like HCl in the previous slide, they're going to interact in that manner. There's a dipole, dipole. Here's a dipole, and there's another dipole. Now I draw this in 3 dimensions, but remember we live in the I draw this in 2 dimensions, but we live in the 3-dimensional world. And so these interactions are occurring not only in the x-axis, but in the y-axis and in the z-axis. There's a whole series of these interactions. Okay, so requirement for a dipole, you must be polar. Okay. Now there is a special kind of a dipole interaction that we call a hydrogen bridging force. It used to be called, and it still is to some extent, is hydrogen bonding. But it's kind of misleading with the term hydrogen bonding because it gave this suggestion that you actually created a bond, which you're not really doing. You have created an interaction. Now, this type of dipole interaction is very specific. It's only true for those hydrogen atoms that are bonded to nitrogen or bonded to oxygen or bonded to fluoride. Okay, we call that NOF, not on file. Nitrogen, oxygen, and fluoride, the hydrogen. Okay, that interaction, there's an additional interaction that's above the dipole-dipole force, and a little bit stronger than the dipole-dipole force, and that's called hydrogen bridging force. But the thing to remember is that we're only talking about hydrogen bonded to nitrogen, oxygen, or fluoride. Otherwise, it's strictly a number 2, a dipole-dipole force. Now, with respect to strength, and meaning how much energy it takes to break up that interaction, hydrogen bridging is the stronger of these 3, followed by dipole-dipole forces. And then number 3, the weakest, is the London dispersion forces, okay? So if you start to think about this for a second, you say, if the hydrogen bridging forces are stronger than, say, the London forces, then, and we're talking about intermolecular forces, that's between, other molecules, this interaction here, that hydrogen bridging force is pretty strong. So it kind of makes sense, you think about it, that it's going to take more energy to break up that interaction when it's hydrogen bridging compared to London dispersion forces, where the interaction there is a little bit weaker, okay? A little bit weaker. So I'll give you a classic example. I'm sure water boils at 100 degrees, H2O. Okay, 100 degrees Celsius to boil. Whereas acetone, if you're not familiar with that, is used in nail polish remover. It's a very volatile. You open up the container and it's, evaporating. I don't have its boiling point. I want to guess in the 40s, 50s, and not 100%. But the point being, it is very much less. The boiling point is much less than water. So one can infer from that is that the interaction, the intermolecular forces for acetone is much less than it is for water. You can take a cup full of acetone and a cup full of water and set it on the bench for a period of time. And I'm sure you've seen, maybe you can try at home, that acetone will evaporate very quickly compared to the water. The water may take a few days for it to evaporate and completely be gone from the container. Whereas the acetone, matter of minutes and not hours, it's gone. Okay, because it doesn't take long to break up the interaction and go into the vapor phase. Not enough energy. The energy requirement is very low. Okay, let me clear this up a little bit. And then we have one last one, number 4, which has nothing to do really with covalent compounds in themselves. It has to do with covalent compound, a covalent compound, specifically in aqueous. Most of the time it's water. We're dealing with water, H2O, and that's the dipole forces that are involved in water. And then we're dealing with some type of an ion, which is a salt. Okay, so we're talking about ionic compound interacting with an aqueous system, which will be water most of the time, 99+% of the time. Okay, has nothing to do with covalent compounds in themselves. So, 4 forces. Let's talk about them a little bit more in detail. Let's talk about dispersion or London forces. These molecules that have this force is kind of temporary, okay? Any compound that you have determined to be nonpolar automatically has London dispersion forces. Now, what we mean by temporary, the best example I can give you is if you were to take a balloon and rub it on your head. Obviously, the surface of our body is loaded with electrons. We got electrons all over the place. You know, drag your feet through some thick carpet and then touch some metal. See what happens. You get a nice little spark, right? Okay, those are electrons. They call it static clean. Sometimes you got bad hair day, your hair poofs out, a lot of static in your hair, or clothes or pants that you kind of hug to your legs. A lot of attraction that way because of the electron density around either the dress or the legs. Now, if you take a balloon and you rub it on your head, you have transferred these electrons onto the surface of the balloon. Now, we all know or seen or even done yourself, you take that balloon, you put it on your chest, and it sticks. And you might wonder, well, why is it sticking? Is this some kind of Harry Potter magical stuff? No, well, no, it's not. It has to do with electrons. We know that electrons have a negative charge, right? And so that balloon full of negative electrons, as it comes to the surface of your chest, which also has electrons on the surface, guess what it does? Negative against negative, it causes those electrons on your surface of your chest and some on the balloon to move away and probably go deeper into my chest, electrons, or in a different direction, resulting in having what's called a positive area, okay? Where there used to be electrons on my chest, there's less electron density, and guess what? It becomes a partial positive on my chest. The electrons have a negative, they attract to each other, and that balloon holds on. Obviously, that doesn't last forever. After a period of time, it resets itself, electrons are dissipated, and that balloon falls off. But the point is that they're temporary. It's not permanent like a dipole on HCl, where that's a permanent dipole. These are temporary dipoles, okay? And this is basically saying what's happening here. We're pushing the electrons. And one thing about this, that when we got nonpolar molecules and we're comparing nonpolar molecules with each other, the thing to remember is this: the bigger nonpolar molecules obviously have more electrons around it, and therefore they will have a more stronger London force. When we are comparing nonpolar molecules with each other, the bigger the molecule, makes sense, more electrons, more London force, okay? And this kind of demonstrates a little bit about what I was talking about with the example of the balloon. You know, you got two, change the color here real quick. Two nonpolar species, you know, they could be diatomic, coming toward each other. Obviously, one of them is here's the electron density, it's kind of came closer to another one. Its electron density pushes the electron density of the other one in the other direction, causing a partial positive here. And guess what? They interact right there. It's a temporary interaction until such time the electrons go back to more of a stable state and they break apart. But this is an example of nonpolar molecules that generate a dipole, a temporary dipole, and it's very weak. And so we call this interaction London dispersion forces, okay? London dispersion forces. And as I stated, they're weak forces. Now, the next one was dipole-dipole forces. Now, in order for this to occur, they must have a permanent dipole. And that example here would be using HCl as an example. Okay. You can see here's the chloride and here's the hydrogen. And obviously there's a dipole going from the hydrogen to the chloride, resulting in a partial negative on the chloride and a permanent partial positive on the hydrogen. Well, when that occurs, then you can see here that the negative, partial negative will interact with the partial positive of another molecule and create this attraction here, this right here. And this attraction, when compared to dipoles, are pretty strong. Compared to London dispersion forces, are strong. All right, so we have interaction here. And but I lost my train here for a second. The requirement here is that you have a permanent dipole. Okay, a permanent dipole. It's because of this of the electronegativity difference between the two atoms. Okay. All right. Now, Larsa, it looks like you're getting a private.
Yeah, just me.
That's okay. Hey, you're gonna get your money's worth. Okay.
Yeah, that's definitely.
Definitely. All right. So anyway, as I was talking about these forces in this, you're gonna have a dipole like hydrochloric acid. Any dipole, any polar bond, this is the result. You end up with a dipole-dipole force. Now, the special case is it wasn't stronger. The requirement here is that, first of all, the dipole-dipole force is much stronger than the London forces. And obviously, it must be a polar molecule or / polar bond, okay? Now, only for those hydrogen molecules that are bonded to nitrogen, oxygen, and fluoride, okay, you have a special interaction. And we call that hydrogen bridging. It used to be called hydrogen bonding, okay, but they're trying to get away from that name because that suggests, right here, that suggests that there's an actual bond, and that's not the case. We're not creating an actual bond. As the other interactions, it is creating an interaction between molecules. If we look at water, water is very polar. Okay, it actually has a double negative here. So we create a strong interaction here, but only for those examples that have hydrogen fluoride, hydrogen oxide, or hydrogen nitrogen. Okay, we form this strong hydrogen bridging force. You can see all the interactions occurring here all the way around. Now, the one thing about this, again, we're three-dimensional. So right now, pictures are here just one-dimensional, but this is going on all the way around, and it's a pretty hefty, strong force. Okay. All right. So that's the hydrogen force. So as far as the strength, we get hydrogen bridging force, number one. Number two is dipole, and then the weakest is the London dispersion forces, okay? London dispersion forces. Finally, the last force is the ion dipole. Well, in order for this to occur, like I stated earlier, you gotta have a ionic compound. And so, either you're going to have both positive and negative cations or ionic compounds, and they're going to be, we're dealing mostly with water. And so what you have here is this depicted in this picture here. You got the sodium cation being solvated all the way around with water molecules. Now, if this was sodium chloride, for example, the chloride would be on the other side, and we will have an interaction here, okay? And another chloride here. So you can see how it's a very complex three-dimensional structure that we observe, or we can measure, and explains a lot of things as to why sodium chloride doesn't evaporate out. It's a salt for one. So to assign ion dipole, you are, what the requirement is obviously a solvent. Most of the time it is water, and you have to have an ionic compound. There's nothing here that deals with covalent compound other than the water part, the aqueous system. But if you got an ionic compound, then you don't have any of the other London dispersion forces or dipole or hydrogen bridging. They have nothing to do with it. They have their own little force called the ion dipole. Okay. All right. And so let me summarize here. And what I'm going to do, I'm probably going to stop it here. If that's okay with you, Larson, and I will continue, I guess, Tuesday, because we have no class on Thursday. Yeah. So bonds, refresh your memory on bonds. We got ionic bonds and covalent bonds, okay? Ionic bonds, as a refresher, it's a metal, non-metal interaction. Okay. Covalent bonds, we got two types. We have a polar covalent bond. That's where we got an unequal sharing, okay? And really, if you look at it in general terms, that example is when we have A bonded to B, two different elements, automatically you have a polar bond. With respect to nonpolar covalent bonds, we have that example. We got A bonded to A, okay? The two elements here are the same. The other example is a carbon-hydrogen bond that fits into the nonpolar covalent bond category. So with respect to bonds themselves. Now the forces, we got London forces that deal with nonpolars. Once you define it as a nonpolar compound, you assign London forces. And if it's not, if it's polar, then it must be dipole-dipole, unless it is hydrogen bonded to nitrogen, oxygen, and fluoride, and then it's hydrogen bridging. Yes, hydrogen, the hydrogen, nitrogen, hydrogen, oxygen, hydrogen, fluoride. Yes, it is a dipole, but it's a special dipole. It's a little bit stronger force between the hydrogen and the nitrogen and the oxygen and fluoride than just a simple dipole-dipole, hydrogen bridging. Then, of course, we have the last one, ion, which is a covalent ionic compound, and a polar molecule, which 9 times out of 10, we're dealing with water there, okay? Now, to be able to assign forces from up here, first of all, we know in this example, if it is a nonpolar species, it's more likely one or two things. All the bonds are nonpolar, okay? Like carbon, hydrogen, nothing but nonpolar bonds, then it is nonpolar, okay? Or it's diatomic, it is nonpolar. Or it can be polar bonds, but the polar bonds cancel each other out, like carbon dioxide. Remember we did that in the arrows, there's two polar bonds, but they go opposite of each other and they cancel out, resulting in a nonpolar molecule, okay? So those three examples, or the tetrahedral, let me give you the other example, where we had tetrahedral example, where we have 4 polar bonds, and let's say carbon tetrafluoride, where you have 4 polar bonds, okay? 4 polar bonds, but because of the configuration of being tetrahedral, all four of them cancel each other out. So this also is nonpolar, okay? So those examples that compounds have polar bonds and the polar bonds cancel out, we end up with a nonpolar molecule. Then we assign London dispersion forces to those compounds. Otherwise, if you have polar bond and they don't cancel out, okay, then you assign to him either a dipole-dipole force, or if it's hydrogen bonded to nitrogen, oxygen, or fluoride, then you assign hydrogen bridging. Okay. So that's kind of summarizes those aspects. Let me clear this up a little bit. All right. You know what? Let me finish. Let me do this table and we'll stop it here. If that's okay with you.
Yeah, that's fine.
Okay. All right. So we have the molecules in the first column. Carbon dioxide, okay, trifluoro, phosphorus trifluoride, HF, hydrofluoric acid, methane. And then we got Ki down here, potassium iodide, and we got AQ, which tells us we're dealing with an aqueous system. Well, you know, the first thing we got to do when we have a series of compounds, they either give you the formula and or they may give you the name, okay? Either way, you get that. You have to figure out, is this thing polar or nonpolar, you know? And sometimes you may need the Lewis dot structure, if we recall how we did that. And if you do, you'll see that we came up with this kind of a structure like I showed earlier. And using all the valence electrons, add them up, coming up with double and triple bonds, wherever we needed to make sure the octet is fulfilled. And we find out that because of the nature of the beads, because the polar bonds are going in opposite direction, carbon dioxide is a nonpolar species, okay? So automatically, once we define it as a nonpolar, automatically London dispersion forces, no questions asked. PF3, we have to first figure out its configuration. And so when we do that, this will be much like ammonium, and we'll do the Lewis dot structures, and we end up with this type of structure here. Whoops. Okay, with the lone pair on the central atom. The moment you see a lone pair in the central atom, you don't have to go any further. It is polar. Okay. It is a polar species. So the next question is, well, since it's polar, obviously we can eliminate London forces, and we can eliminate number 4 with the ion dipole because there's no ion here. So the only two choices we have is either a dipole-dipole or a London bridge force. Well, it can't be London bridge because London bridge only deals with hydrogen bonded to nitrogen, oxygen, and fluoride, and there's no hydrogen here. So the only thing left is dipole-dipole interaction. See? So in the process of elimination, you can assign a interaction, a force to that molecule. We have HF, the fact that you got two molecules, two different molecules, no question, it is polar. Okay. But now, as we did with the previous one, it's not London, obviously, and it's not ion dipole. So we have to decide dipole-dipole or hydrogen bridging. The fact that you have hydrogen bonded to fluoride tells you it's not dipole-dipole, but it is hydrogen bridging force because it's hydrogen bonded to fluoride. Methane, CH4. If you do the Lewis dot structure, you get a tetrahedral configuration. Plus, not only that, you got carbon-hydrogen bond, okay? And as we stated, any carbon-hydrogen bond is nonpolar. All 4 bonds are nonpolar, therefore we have a nonpolar molecule. automatically the only force it has is the London forces. And then the last part is Ki. You see it's ionic, and it's AQ, meaning aqueous. So the only logical choice is ionic in polar water. That's it. It's not really polar or non-polar. It's just ionic in polar water. And the stronger force associated with that is simply the ion dipole force. Okay. So with that, once we able to assign a particular force to the molecule, specifically dealing with just the, let me clear this up here, just the ionic compounds, which are these, with the covalent compounds. Once we assign this, now we know with respect to strength, who's the strongest. H, hydrogen bridging, is the strongest force, okay? The weakest force is London and London, okay? And then the intermediate force is dipole. So now we can do predictions, and we can say that methane and carbon dioxide, based on their London force, would boil at a lower temperature than the others because the London forces are very weak, okay? And we will say the molecule HF would have the highest boiling point because it has the strongest force, and therefore the molecules are held onto each other much stronger than the other forces. So it takes a lot of energy to break that force apart, which means the temperature would be much higher as far as its boiling point. Okay, well, let me stop it here, and we'll continue with this Tuesday. So let me write this down. Don't forget, we are on chapter 14. Okay. All right. Do you have any questions?
Not so far. I'm good.
Okay.